All right, hi everyone, I'm Tony Arcieri, thank you for coming. This is Frontiers in Cryptography. So today's talk is kind of two talks in one. I'm going to start out by talking about the past. I think one of the best ways to see into the future is by looking into the past. And then I'm going to talk explicitly about the future with kind of a theme around searching and computing on encrypted data on ciphertexts. So quick disclaimer, I am not a cryptographer. I prefer to self-identify as a cypherpunk, or I think I put post-cypherpunk in my bio. So I'm going to ask you to hold your questions until the end, both for the sake of time and because it's quite likely I won't actually know the answer. So let's start out by looking into the past. So how many people came to Strange Loop last year and saw Philip Wobbler's talk propositions as types? So I'm kind of borrowing from his theme there. If you didn't see it, it was a great talk. I recommend watching it online. So to start out with, I'm going to ask this question: how would aliens encrypt? And kind of this idea is, are the cryptographic constructions we use today invented or discovered? Are they things that aliens on a completely different planet would independently rediscover themselves? So what do I mean by that? Well, I don't necessarily mean that they're using the exact same ciphers we are. Some cryptography is more invented than discovered, to be certain. But there are certain algorithms I think aliens would independently rediscover completely on their own. So one of these algorithms is Diffie-Hellman. It's Martin Hellman and Whit Diffie there. And, oh wait, who's this guy? Oh, okay, so that's Ralph Merkle. Somehow he always gets cropped out of this photo. He was actually the first person in the public community to come up with a public key cryptography algorithm. It was called Puzzles. And that kind of inspired the ideas of Diffie and Hellman to develop this Diffie-Hellman algorithm. So this is a public key algorithm for doing key exchange. The other one, which you might be a little more familiar with, is the RSA algorithm. So here are the three cryptographers who invented that. So here we have this sort of textbook history of public key cryptography, that these two trifectas of cryptographers came up with these algorithms. The only problem is that isn't actually true. Neither of these algorithms were originally discovered by their eponymous cryptographers. So actually they were first discovered at GCHQ, which is kind of the British equivalent of the NSA. So this guy, James H. Ellis, had been working on this problem for a long time. Originally came out of during World War II. They wanted to build identify friend or foe systems for things like aircraft. So they wanted a way to be able to verify a signature, effectively, as we would call it today, without holding a secret key that would let you sort of generate these identify friend or foe proofs. So he came up with the existence proof for public key cryptography. So he described a incredibly impractical system for doing public key cryptography, but he proved it was possible. And these other two cryptographers, Clifford Cox and Malcolm Williamson, sort of independently came up with the algorithms we know of as Diffie-Hellman and RSA before Diffie-Hellman and RSA. So these are kind of strange and spooky problems. They have this spooky connection through this thing called the hidden subgroup problem. So they're sort of like two sides of the same coin. So RSA is based on the difficulty of factoring numbers. Diffie-Hellman is based on something called the discrete logarithm problem. And they share these group homomorphisms to where if you solve one problem, you solve them both. So one of the best known algorithms for solving factoring is something called Pollard's row algorithm. So he originally created it to solve factoring, but then a few years later, he made a very similar algorithm that solves the discrete logarithm problem. Another interesting one, so elliptic curves are kind of the best modern way to do public key cryptography right now. This other cryptographer, Lenstra, came up with a way to use elliptic curves to factor numbers, and it remains still one of the best ways to do factoring. And then a little bit later, Shor's algorithm provided a way to factor numbers on quantum computers in an almost disastrous way. Fortunately, we haven't built large quantum computers yet. So maybe you're thinking, okay, Tony, that's great. So public key cryptography is based on math, but what about symmetric encryption, right? That's just a bunch of bit twiddling, right? So certainly aliens wouldn't come up with the same symmetric encryption ciphers that we did here on Earth. But actually, I think maybe there are some fundamental components of symmetric encryption they may independently rediscover on an alien world. So this is something called a Feistel network. It's based on an earlier idea from Claude Shannon's where it called a product cipher, and it's a way of turning a pseudo-random function, so there's F's there, so a pseudo-random function takes some input and it produces a mangled output that in theory you can't reverse back into the original ciphertext, or the original plaintext. So this takes those pseudo-random functions and builds a network out of them such that we get something called a pseudo-random permutation. And that lets you take a piece of plaintext, turn it into ciphertext, and then turn it back again into the same plaintexts. So Feistel networks were the basis of ciphers such as the data encryption standard, or DES. So in conclusion, I think cryptography may actually be more discovered than invented in a lot of cases. I think there are ciphers we're making here on Earth that aliens would independently rediscover on alien worlds. All right, on to the future, which is probably the part you came here to see. So typically, we'll have a client and a server, and we may have this encrypted pipe. You definitely should have one of these today. That'll prevent any sort of attackers out there on the internet from recovering your plaintext. And what we like to do is send that plaintext over to the server, and then the server can provide us all these cool services. We can search things, the server can organize them for you, it can perform analysis, and that's all great. And then when the server is done, it's going to give you a plaintext result. Again, over that TLS channel there, I'm just going to omit this for the rest of the slides, just kind of assume that's there. So then, something that I think a lot of people would like to switch to is typically called end-to-end encryption. And this is where a key is held by the client, and then the client encrypts client side. We send the ciphertext over to the server. The problem is there are all these things we want to do, and typically we just can't do any of those to ciphertext. So what would really be nice is to have a special type of ciphertext that exposes some of the properties or some of the structure of the original plaintext while still keeping the data confidential. So that we could send that over to the server, perform some of these operations, and either get back a result that is plaintext or potentially get back a ciphertext result. So a word of caution before I proceed. This is sort of science experiment stage. It's very cutting edge cryptography. And generally, a lot of the systems people have tried to build this way have been broken. So the main problem we run into is this idea of indistinguishability. So I'm going to give a little, your typical adversary model diagram here. So the part of the cartoon devil here will be played by former NSA Director General Keith Alexander. So typically what we want is this property called indistinguishability. So this is in cryptography typically phrased as something called a semantic security game. And the idea is an attacker who can potentially even provide the plaintext in these cases. So let's say Keith Alexander here is giving our encryption oracle plaintext A and B. The idea is if we have an indistinguishable cipher that Keith there cannot tell with greater than chance accuracy which of those ciphertext was produced from the plaintext, even if he's in control of them. So there have been a lot of actual production systems people have tried to build using these techniques. Here's a list of some of them. And the problem is they keep getting broken over and over. So I might be using the word broken a bit liberally. The creators of some of these systems would argue that they're just fine and that the people pulling off these attacks were doing things that were out of the scope of what they said they're allowed to do. But I'm kind of a realist. I think people are going to misapply cryptography all the time, so I kind of just prefer things be nice and solid. So you may have seen this article. So the researchers who produce these systems kind of play these cat and mouse games with each other where they keep breaking each other's systems. And there are some particularly fun ones with CryptDB where they were able to break it with frequency analysis. So a word of caution, if you want to run out and play with this stuff, please consult a cryptographer before you try to. So I'd like to give an example of the type of system it would be interesting to build with this, with these sort of techniques. So it's a encrypted email service. You can imagine something like Gmail, where we don't want to store all of the messages, like your entire email history on your smartphone. We want the server to be able to hang on to these things, but still provide services like ordering, so we only want to see the latest messages unless we're going back in history. We want to be able to do full text search. We want server-side spam detection, so the server could decide whether or not something is spam without having to send it to the client first. And we want to be able to filter and prioritize emails. So the first type of technique I'm going to talk about is property-preserving encryption. So there are many different types of property-preserving encryption. There's another type I'm not going to talk about called format-preserving encryption. But the main useful one, I think, for these sort of encrypted search cases is order-preserving encryption. Now, the original conception of order-preserving encryption is broken, so you don't want to use that. The more interesting one is this thing called order-revealing encryption, which came out of Dan Bonnet's group at Stanford. And the idea of this is we create ciphertext in such a way that there is a public function we can hand any two ciphertexts to, and it will kind of give us some sort of lexicographic order. Now, the interesting thing about the way they formulated order-revealing encryption is there is no way to tell if two ciphertexts are encryptions of the same plaintext. So this kind of upholds that indistinguishability or semantic security property that I was originally talking about was desirable. It also lets us do things like range queries. So we can create an encrypted range and then query the ciphertext across that. So really quick, here is the paper. So this is the latest order-revealing encryption paper. If you're interested in learning more, I recommend checking that out. So the next thing I'm going to go into is actually amalgamation of several techniques, which I'm going to cover later, but it should give you the general idea of what this will provide. So we want to do full text search on encrypted documents. So this is a bit tricky. There have been many attempts at implementing this that have been shipped to production or the basis of startups and actually completely broken. So to start off with, I'm going to show you one technique to do this, which is broken. This is kind of the naive method that people might come up with, just trying to assemble a system like this from existing cryptographic primitives. So what we're going to do is a client is going to encrypt a document and at the same time also build an inverted search index that can be updated server-side. So the way they're going to do that is they're going to take every single word in this document, encrypt the word deterministically, so that each word always results in the same ciphertext. And then we're going to encrypt the document as well, using an algorithm like AES or something like that, and put it in this document store. And then the server is going to retain this inverted index of which deterministically encrypted words map to which documents. So the thing about this is, let's say old Keith's up there again, and Keith is able to, if this is an email system, he's able to send us email. So Keith can send us some sort of email that contains some word that he's curious about. And then when the encrypted version gets sent back over to the server, since he's the NSA and he completely owns the server, he's able to look at how the index changes in response to the message that he sent. And using techniques similar to this, it's possible to completely break such systems. So in summary here, the basic idea is building this index of these tokens to the documents they point to, and then they're broken because we lose this property of indistinguishability. So to build secure, searchable symmetric encryption, we're going to need more tools. So one of these is called Oblivious RAM, or ORAM. And the idea of this is, instead of Keith being able to observe those incoming ciphertexts and correlate which ones come in based on the message he sent, we mask the data access patterns to look completely random. So yeah, as I said, this can be a basis for higher level primitives, including searchable symmetric encryption. But the problem is, by doing all of these spurious data accesses, we're going to lose some performance. So next, I'm going to talk about functional encryption. So this is going to use something called lattices. So perhaps you've heard of lattices in distributed systems for implementing things like vector clocks or CRDTs. And you're thinking, it's a lattice, I know this. But unfortunately, this is not the same type of lattice you're thinking of. To make things especially confusing, both of these lattices come out of abstract algebra. So they come out of different subdisciplines. The ones I'm talking about come out of group theory. Yeah, I'm not even going to attempt to explain that. But, what lattices allow us to implement is something called functional encryption. So with functional encryption, what we can do is the server could provide a spam score function, and then the client can actually encrypt that function so it works on ciphertexts, and then hand that over to the server. So in this way, the server can then apply that function to ciphertext, get this spam score out, and therefore decide whether or not an email is spam. So there's a subset of functional encryption called homomorphic encryption. And the idea here is we have certain operations we can perform on the plain text, and then there are corresponding ones that are a direct mapping of the operations on the plain text that apply to the ciphertext. So there are two sort of families of homomorphic encryption. It's called partially homomorphic. So the idea here is there are certain subsets of operations where this homomorphic property holds. So we may be able to add two ciphertexts together and get a ciphertext, which is the encryption of the result of that addition. And then there's also the holy grail of homomorphic encryption, which is arbitrary computation on ciphertext. So effectively, Turing-complete functions. So before I get you too excited about this, there is a huge drawback to fully homomorphic encryption, and that is not very fast. This is a quote from Dan Bernstein, he designed all the ciphers that we're just about to start using in TLS. So I've kind of taken this quote out of context, but I think it gets the idea across. So some of the big papers on homomorphic encryption, this is the BGV paper. So this was one of the first examples of a fully homomorphic encryption system that is approaching practicality. So I don't have exact numbers for this, but I think it's close to 1 million times slower than the equivalent computation without homomorphic encryption, right? This is another interesting paper. They describe this technique they call indistinguishability obfuscation. So it's a way to take algebraic circuits and effectively obfuscate them such that two obfuscations of the same circuit are indistinguishable. So you could not tell whether or not the same circuit was encrypted twice. And this can be used to implement both functional encryption and fully homomorphic encryption. A more interesting library in that this is one you can go download and play around with is called Seal. So this comes out of Microsoft Research. I don't believe this library is fully homomorphic, but it provides a way to do all sorts of algebraic operations on ciphertexts. And then Microsoft Research took some of those ideas and created this cool thing called CryptoNets. So this is a machine learning platform based on neural networks that was designed to operate on ciphertexts. So this is probably a more practical example of what fully homomorphic encryption could allow you to do. So I think in this case, it was like they were trying to move a healthcare system into the cloud. And due to HIPAA and things like that, operating on patient data on computers you don't control would not be HIPAA compliant. So they built the system that allows allows a machine learning system to make predictions about patients based on their encrypted healthcare history. So since fully homomorphic encryption is so slow, people have been looking at other ways to do this. So one of the things we can do is, instead of using all of this fancy math, we can use trusted hardware instead. So there are a couple of upcoming implementations of this that are pretty interesting. Intel created a system called SGX. AMD has made a completely incompatible system called SEV. Intel has shipped SGX on Skylake. SEV is not yet shipped. But the idea of this is you can run a program inside of an encrypted region in main memory. So typically main memory has been like wide open to all sorts of things. Hardware can do DMA, for example. So the idea of this is they want to reduce the trusted footprint of hardware such that the only piece you have to trust is actually the CPU. So you don't have to trust the RAM, you don't have to trust any of your hardware that can do DMA. All you have to trust is the CPU. And the thing is, really when it comes down to it, you always have to trust the CPU. If you're running a secure program on a poison CPU, like game over, you already lost. So I think this is an interesting technique. A lot of the ways Intel has implemented it have raised some criticisms. So what Intel is doing right now is requiring Intel sign off on every single program that you want to run under SGX. So there's some good reasons for doing that. Without it, people could create encrypted malware and things like that. So, this, as much potential as this has to help the good guys, I think, has just as much malicious potential. But at the same time, I think a lot of the use cases where people would like to use it, they don't necessarily want to hand every single program they ever intend to run over to Intel first. Maybe they just want to keep their programs confidential. Maybe they kind of look at Intel as the bad guy, even though they want to use the feature. But either way, I think I wouldn't actually recommend starting to use SGX quite yet. I'd give it a little more time to settle down. But one of the interesting features it has is an attestation protocol. And the idea of this is when you hand your program over to the CPU has a key with which it can sign effectively the results coming back from this program. So by doing that, as you're talking to this program, let's say over the internet, and you want to make sure the CPU is actually running the program you gave it, it has this protocol that allows it to tell you that it is actually running the program you intended it to. So the main sort of interesting practical application I've seen done with this is this thing called Microsoft VC3. So VC3 is a implementation of Hadoop MapReduce that works on encrypted data stored in HDFS. So the thing I absolutely love about this is I hate Hadoop security. So if any of you have ever tried to deal with Hadoop security, it's a nightmare. It offers a ton of features for doing security. It has its own sort of transparent encryption feature. It has Kerberized access control. But it's so complicated and so difficult to understand that it's very difficult to deploy Hadoop securely correctly. So what VC3 does is it reduces the trusted footprint of Hadoop down to the actual MapReduce operations themselves. So for the most part, you don't really have to care about most of the security aspects of Hadoop. It's going to MapReduce your data, pull it into one of these encrypted enclaves, decrypt it there, perform the MapReduce operation, and then encrypt the results, and then put that back in your HDFS. So as far as I know, this is yet another sort of science experiment. I don't think they're actually shipping this, but it seemed interesting to me. So last, I wanted to talk about something completely different. At the beginning, I had mentioned Shor's algorithm and how it can be used by quantum computers to solve some of these problems. So Shor's algorithm is one of these that illustrates a group homomorphism between factoring and the discrete logarithm problem. And by using this, since these problems share this homomorphism, we've completely lost at this point. Using this one algorithm, quantum computers can break all of the public key cryptography we use today. So the thing about Shor's algorithm is it requires much larger quantum computers than we have built right now. For the most part, the quantum computers we have built are very small and do not seem to be outpacing their classical counterparts. So you may have seen the D-Wave machines, which are not full quantum computers. They're what's known as an annealing machine. And they have generally been losing out to simulations of quantum annealing running on classical computers. But the thing is, there are a lot of practical applications of quantum computing that are starting to drive the development of quantum computers. And I don't think that's necessarily cryptography. So someone like the NSA would probably love to have a giant quantum computer, but I really doubt they have built one yet. But beyond that, beyond these large government organizations that are interested in wide-scale breaking, I don't think cryptography is really going to drive the development of quantum computers. But there are other fields where I think they could really be helpful, things like chemistry and biology, and running simulations of those. So I think these other fields are actually going to drive the development of quantum computers. And as soon as we reach, it's going to be the thousands of qubits. Right now, depending on who you ask, we're at about 4. There may be slightly larger ones, but to break a ECC key, it's close to 2,000 qubits. To break something like an RSA key, that's 2048 bits. It's going to be about 4,096 qubits. So we're still nowhere close to actually building quantum computers large enough to solve these problems. but as soon as we do, we can solve all of these classical problems that we have used to build public key cryptography systems. Just as a ballpark number, different people say different things. It seems like at least a decade is a fairly reasonable estimate of the minimum amount of time before we'll see a quantum computer big enough to actually run these algorithms on the kind of public key algorithms we're using today. So there are a number of different candidates for replacing algorithms like RSA, ECC, Diffie-Hellman, with algorithms that cannot be solved by a quantum computer. So the most promising now, just in terms of there are various trade-offs, like how big are the keys, how long does it take to compute. So lattices, as I mentioned earlier, generally seem to be the way things are heading. Different people have different opinions on this, but the main algorithm that seems to be the most popular now is this one called the ring learning with errors problem. So the same problem, the learning with errors problem, is also used to implement fully homomorphic encryption. But this is the main algorithm that people seem to be talking about and implementing. There's another one called ntrue. The only problem with it is it's patented, but otherwise it's actually faster than elliptic curve cryptography we use today. Another approach to this is called isogenies. So there's this system called super singular isogeny Diffie-Hellman, which takes elliptic curve cryptography, applies isogenies to do this, and produces a post-quantum version of effectively elliptic curve Diffie-Hellman exchange. And then the last one, I mentioned Dan Bernstein earlier, so he's been doing a lot of work on post-quantum cryptography as well. So it's based on linear codes. So the algorithm is called Macaleese, and Dan Bernstein's version of it is called McBits. But the most interesting thing, I think, is this is actually shipping in Chrome now. So if you pull up your Chrome inspector and go look at the actual algorithm being used to exchange keys in TLS, they have added a post-quantum algorithm. So this is New Hope that I was talking about earlier. So they built a hybrid pre-quantum, post-quantum key exchange algorithm that is based on New Hope and elliptic curve, traditional elliptic curve Diffie-Hellman. So you may start seeing this in your browser today. So that's it. I hope what you take away from this is that I think cryptography is going to become increasingly important in database development. I think we're going to start seeing more of these databases. So, for example, Google has published an encrypted MapReduce client that's using partially homomorphic encryption. Microsoft has shipped similar features in SQL Server based on their research in Cypherbase. So I think in the coming years, we are going to see databases that are operating routinely on ciphertexts, and I think this is going to be the future of databases. All right, thanks. Yeah. All right, I'll go ahead and take any questions now. Yes. Yeah, so this is all, the question was how do we transition from pre-quantum to post-quantum cryptography? So the nice thing is this is already built into TLS. So TLS supports this idea where the client will send over its supported algorithms and go, hey, I support all these, and then the server can pick one they mutually agree on. So you just, if both sides support a post-quantum algorithm, the client just advertises it, the server picks it, you have to prioritize it. But that just, you kind of get that for free with TLS, which is pretty cool. And actually, the Google example is actually using a different transport encryption algorithm called QUIC, which was developed in-house by Google. They're trying to standardize it, but it supports the same sort of thing. So yeah.
Are the post-quantum algorithms proven to be safe against quantum attacks, or we just don't know any attacks?
Yeah, so the question was, are post-quantum algorithms known to, or provably secure? So the answer is no. A lot of them seem kind of shaky, which is why people are somewhat hesitant to ship them today, especially if there isn't a pre-quantum backup. So what they're doing today is kind of hedging their bets in terms of, we'll use a pre-quantum algorithm, and then in parallel, we'll run the post-quantum one. So both of these algorithms do key exchange. So you can kind of do pre-quantum and post-quantum key exchange side by side, and then you feed the results of both of those into something called the key derivation function. And so you get effectively the security of both. It will be at least as secure as the strongest of the two. Any other questions? All right.